Could you journey to tomorrow or revisit yesterday? The dream of time travel captivates us, from the DeLorean in Back to the Future to the TARDIS in Doctor Who. But what if this was not just science fiction? We are about to explore 30 scientific and speculative theories that could actually make it possible. By the end, you will understand the real physics and philosophy that might one day unlock the secrets of time. We will investigate how black holes could be portals and whether you could change the past without creating a paradox. What single moment in history would you choose to witness for yourself? Einstein shattered our common sense view of time as a universal constant. His theory of special relativity revealed that time is not a rigid backdrop for the universe but a flexible fabric, deeply intertwined with motion. The faster you move through space, the slower your clock ticks relative to someone who is standing still. This phenomenon is known as time dilation, and it is not just a mathematical quirk. It is a proven, measurable reality that affects our daily lives. To grasp this, picture the famous twin paradox. One twin stays on Earth, while the other embarks on a space voyage at a significant fraction of the speed of light. From the Earthbound twin's perspective, the ship appears to move in slow motion. The astronaut twin's heartbeats, thoughts, and aging process all seem to crawl. After a long journey, the spacefaring twin returns home, only to find their Earthbound sibling has aged decades more. The traveler has effectively journeyed into the future. This is not science fiction. We have confirmed it with incredibly precise atomic clocks. When scientists placed these clocks on commercial airplanes flying at high speeds and compared them to identical clocks on the ground, the flying clocks ran ever so slightly slower. This same effect is crucial for the Global Positioning System, or GPS. The satellites orbiting Earth move so fast that their onboard clocks fall out of sync with ground clocks by a tiny fraction of a second each day. If engineers did not constantly correct for this relativistic time warp, your phone's map would be wrong by several miles within minutes. So, the very first step toward real-time travel is already happening above our heads, a subtle but constant journey into the future for everything that moves. Einstein took this bizarre idea even further with his theory of general relativity. He proposed that gravity is not a force in the traditional sense, but a warp in the fabric of spacetime itself. Think of spacetime as a vast, flexible rubber sheet. A massive object like our Sun sits in the center of this sheet, creating a deep depression. The planets orbit not because they are being pulled by a mysterious force, but because they are following the curved contours of this cosmic dimple. This curvature does not just guide the paths of objects, it directly influences the flow of time. The stronger the gravity, the more space-time is warped, and the slower time itself passes. This is gravitational time dilation. We can measure this effect right here on Earth. Scientists have used atomic clocks of incredible precision, placing one on the floor and another just a meter higher. The clock on the floor, experiencing a slightly stronger gravitational pull from being closer to Earth's center, actually ticked slower than the one raised higher. The difference is minuscule, but it is undeniably real. Now amplify this effect to an extreme. Picture the edge of a black hole, a place where gravity is so intense that not even light can escape. Here, the warping of spacetime is absolute. If you could hover near a black hole's event horizon, your clock would crawl to a near standstill relative to the rest of the universe. Spend what feels like a single hour in that immense gravity well, and when you return to Earth, you might find that thousands of years had passed for everyone else. You would have made a colossal leap into the future. This is not just theoretical. The movie Interstellar depicted this concept with stunning accuracy. When the crew visited a planet orbiting close to a supermassive black hole, every hour they spent on the surface translated to 7 years passing for an astronaut waiting in orbit. This is the ultimate expression of gravitational time travel, a one-way ticket to tomorrow written into the very laws of physics. but gravity's warping of spacetime hints at an even more incredible possibility. What if the fabric of the cosmos could be folded, creating a tunnel that bypasses normal space and time entirely? This is the theory of wormholes, often called Einstein-Rosen bridges. Picture the universe as a vast sheet of paper. To get from one edge to the other, you would normally have to travel the entire long, flat distance. But if you could fold that paper, bringing two distant points together, you could punch a hole through the connection, creating a shortcut. A wormhole is that cosmic tunnel, a bridge that could connect not just different places, but potentially different moments in time. The entrance might be in your backyard, while the exit could open up near a star 1,000 light years away or in the distant past. The concept emerged directly from Einstein's equations, a mathematical possibility that suggests spacetime can be threaded like a needle. The problem is that these theoretical bridges are notoriously unstable. According to our current understanding, a wormhole would snap shut the instant anything tried to pass through, crushed by the very forces of gravity that created it. To keep one open for travel, you would need a truly bizarre substance, something known as exotic matter. This is not antimatter or dark matter, but a theoretical material that possesses something called negative energy density. Think of it as a kind of anti-gravity foam, propping the tunnel's throat open against the immense pressure trying to collapse it. If such a material could be found or created, and if the engineering challenges of building and stabilizing a tunnel through spacetime could be overcome, the possibilities are mind-boggling. Stepping through a wormhole could be like stepping through a doorway into another era. You could walk in one end in the 21st century and emerge from the other end in the age of the dinosaurs. Yet this incredible power comes with profound questions. What if you stepped through and prevented your own grandparents from meeting? Would the universe find a way to stop you, or would you unravel the very timeline that led to your own existence? The wormhole is a tantalizing key, but it may unlock paradoxes we are not yet prepared to face. While wormholes offer a potential doorway through time, another theory suggests the universe itself may have woven ready-made loops into its fabric. These are cosmic strings, theoretical scars from the universe's fiery birth. In the first moments after the Big Bang, as the cosmos cooled and expanded, space-time itself may have undergone a phase transition, much like water freezing into ice. And just as ice crystals can form with cracks and fissures, this cosmic freezing might have left behind unimaginably thin, incredibly dense threads of pure energy stretching across the entire universe. A single cosmic string would be narrower than a proton, yet a single inch of it could weigh more than a mountain. Their gravitational influence would be so profound that they would act like razor wires slicing through the cosmos, warping the space around them into deep gravitational wells. Now imagine two of these cosmic underwires, these infinitely long and massive filaments, passing by one another at a significant fraction of the speed of light. Their combined gravitational fields would twist the fabric of spacetime into an impossible knot. The mathematics of general relativity shows that this specific, violent dance could create something known as a closed timelike curve. This is a path through spacetime that loops back on itself. If you were to follow this curve, you would travel on a journey that inevitably brings you back to your own past, like an ant walking along a Möbius strip, forever retracing its steps through time. You would not need a machine, just a spacecraft capable of navigating this pre-existing cosmic roller coaster. The energy required for such a phenomenon is almost beyond comprehension, harnessing the raw power of the universe's infancy. The sheer scale is humbling, a reminder that the keys to time might not be something we build, but something we discover, woven into the grandest structures of existence. But what would it feel like to step onto such a loop? Would you be a passenger on a predetermined track, watching your own history replay itself, or could you interact with the past you find there? Frank Tipler took this idea of twisting the cosmos to its absolute extreme. He proposed a machine so immense and powerful it could literally stir the pot of spacetime itself. Imagine a cylinder not of metal but of some impossibly dense material, perhaps compressed neutron star matter. This cylinder would need to be infinitely long, spinning at a blistering speed approaching half the speed of light. According to the equations of general relativity, such a colossal, rotating object would not just sit in spacetime. It would actively drag the fabric of the universe around with it, like a spoon spinning in a vast vat of honey. This phenomenon is known as frame dragging, a subtle effect we can even measure around our own rotating Earth, though on a tiny scale. Around a Tipler cylinder, this dragging would be so violent it would twist spacetime into a knot. The cylinder would carve a groove in reality so deep that time itself would be pulled into a circle around it. The path to the past would not be a straight line but a complex spiral. A spacecraft would need to navigate a precise corkscrew orbit around the spinning cylinder, riding the whirlpool of distorted time. Completing this spiral loop would not just bring you back to your starting point in space, it would bring you back to a moment before you even began your journey. You would have traveled into your own past. The sheer scale of such a construction is beyond human comprehension. An infinitely long cylinder is, by definition, impossible to build within our finite universe. And just like with wormholes, the cylinder would likely need to be made of exotic matter to prevent it from tearing itself apart under its own unimaginable gravitational forces. The Tipler cylinder is a testament to the power of pure mathematics, showing us that the laws of physics might permit time loops, even if the engineering required to create them belongs to the realm of gods, not humanity. It forces us to ask a haunting question. If you could spiral back and witness your own launch, would you be watching a ghost, or would you become a part of a cycle with no true beginning? The ultimate expression of gravity's power over time is not just a slow drift into the future, but a violent, chaotic gateway. A standard black hole with its crushing central singularity offers only a one-way trip to oblivion. But what if some black holes are not dead ends but revolving doors? Enter the Kerr black hole, a spinning vortex in the cosmos. Unlike its static cousin, a Kerr black hole does not just pull spacetime inward, it drags the entire fabric of the universe around with it, creating a maelstrom of distorted time and space. This furious rotation shapes the black hole into a dynamic structure with two key features. The first is the ergosphere, a flattened region of twisted spacetime surrounding the event horizon. Here, the drag is so powerful that nothing can stand still, not even light. Everything is forced to move with the black hole's rotation, a testament to its raw, churning energy. But the true mystery lies deeper at the black hole's heart. Instead of a single, infinitely dense point of no return, a Kerr black hole contains a ring singularity. Picture a loop of unimaginable density, spinning so fast that its center is not a point but a hole. The mathematics of general relativity suggest that this ring could act as a portal. If you were to fall into a Kerr black hole and somehow navigate the turbulent forces, you might not be crushed. You could, in theory, pass through the ring's center. Where would you emerge? The equations point to a mind-bending possibility, a gateway to another universe or a different time in our own. This potential for travel is tied to the closed timelike curves that are thought to form deep within the black hole's inner horizon. Within this hidden region, the normal flow of time could break down completely, twisting into loops that might carry you into your own past. The wild speculation is that falling into a specific trajectory within a Kerr black hole could spit you out elsewhere and elsewhen. Yet this incredible promise comes with extreme and unknown dangers. The inner horizons might be regions of intense, destructive energy. The physics at the ring singularity itself are a complete mystery, governed by a theory of quantum gravity we do not yet possess. You might be torn apart by tidal forces or vaporized by a firewall of radiation long before you reach the ring. A journey into a Kerr black hole would be the ultimate gamble, a leap into a cosmic whirlpool where the prize could be the entirety of time and space, but the price is almost certainly annihilation. But what if you could travel faster than light without breaking the universal speed limit? The solution may lie not in moving through space, but in moving space itself. In the 1990s, physicist Miguel Alcubierre proposed a radical idea, a warp drive that would sidestep Einstein's rules by contracting the fabric of spacetime in front of a spacecraft and expanding it behind it. Imagine your vehicle is a surfer, not paddling through the ocean, but sitting on a board while the wave itself carries you forward. Within the warp bubble, the ship would be stationary, at rest relative to the space immediately around it. No crushing G-forces, no relativistic side effects. Yet, the bubble of spacetime containing the ship would be propelled forward at speeds that could exceed light, because spacetime itself is not bound by the light-speed barrier. The entire universe ahead would be squeezed together, while the universe behind would be stretched apart. You could cross galactic distances in weeks or days, arriving at your destination without having aged a second. This manipulation of spacetime does not just shrink the galaxy, it profoundly twists our experience of time. Due to the relativity of simultaneity, the sequence of events becomes tangled for observers inside and outside the bubble. For those on the journey, the trip might feel instantaneous, but back on Earth, centuries could have passed, propelling the travelers into the far future. Some calculations even suggest that by carefully steering the warp bubble on a complex loop, you could create a closed time-like curve, effectively arriving back home before you ever left. This is not merely moving fast, it is folding the timeline itself. The catch is almost as immense as the promise. To create and sustain this warp bubble, you would need a shell of exotic matter with negative energy density, a substance that pushes rather than pulls, creating the anti-gravitational pressure required to inflate the spacetime behind the ship. The energy requirements are staggering, initially calculated to be equivalent to the mass energy of entire planets. Later refinements have suggested that a donut-shaped ring might lower the need significantly, but it remains far beyond our capabilities. The Alcubierre drive is a beautiful mathematical daydream, a proof that the laws of physics might not forbid the stars. It suggests that the ultimate engine for time travel may not be a machine that moves through time, but one that moves time itself. While warp drives twist the fabric of spacetime, quantum mechanics suggests the entire universe is constantly splitting apart. At the tiny, subatomic level, particles exist in a haze of probability. An electron is not in one place, but in many places at once, a state known as a superposition. Only when we observe it does this cloud of possibility collapse into a single, definite location. But what happens to all those other possibilities, the places the electron could have been? The many worlds interpretation offers a staggering answer. It proposes that the universe does not choose. Instead, every single quantum event, every random flicker of a particle, causes reality to branch into multiple parallel timelines. In one world, the electron is here. In another, it is there. Both are equally real, unfolding simultaneously in a vast, ever-expanding multiverse. This means that at this very moment, an infinite number of versions of you are living out the consequences of every choice you ever made and every choice you did not. Your life is a constantly forking path with new branches sprouting from every quantum fluctuation. Now, consider what this means for time travel. If you built a machine to journey into the past, you would not be returning to your own single, fixed history. You would be arriving in the past of a parallel universe, a branch that split off from your own the moment you arrived. In this new timeline, you could do anything. You could prevent a historical tragedy or even confront your own grandfather before he had children. There would be no paradox. In that branch of reality, you might succeed, and that version of you would never be born. But the original timeline you came from remains untouched and unchanged. Your own personal history is safe, preserved in its own separate universe. Your actions do not erase your past, they simply create a new future in a new world. This theory elegantly sidesteps the terrifying logic of the grandfather paradox. You are not changing history, you are merely switching tracks on an infinite cosmic railway. The headache of causality, of being unable to alter the past without destroying the reason for your journey, simply vanishes. You become a tourist in the landscapes of what might have been, free to explore any possibility without the fear of unraveling your own existence. But this freedom comes with a profound and lonely question. If every choice spawns a new world and every moment creates an infinity of selves, then who are we really? Are we just one thread in an unimaginably vast tapestry, forever separated from the other versions of our lives by the unbridgeable gaps between worlds? This looping path through reality is known as a closed timelike curve. Imagine drawing a line on a map of your life, a line that represents your journey through time. Normally, this line moves forward, never looking back. A closed timelike curve is a path that bends so dramatically it circles back, allowing you to physically return to a point on your own timeline. You could start your day, have breakfast, and then take a walk that somehow leads you back to the moment before you even took your first bite. These are not science fiction. They are rigorous mathematical solutions to Einstein's equations of general relativity, permitted under very specific and extreme conditions. One scenario involves a universe that is rotating as a whole, its collective motion twisting spacetime into global loops. Another, more localized possibility exists in the violent vicinity of massive, spinning objects like the Kerr black hole we just discussed, where the drag on spacetime becomes so severe that time itself is forced into a circle. The implications are as profound as they are bewildering. What would happen if you followed such a curve and met your younger self? Could you shake your own hand? Could you pass a note to the person you were with instructions that change everything? This is where the classic grandfather paradox becomes terrifyingly immediate. If you travel back and somehow prevent your own birth, how could you have ever existed to make the journey in the first place? The universe seems to have a logical allergy to such inconsistencies. This is why the brilliant physicist Stephen Hawking proposed his chronology protection conjecture. He essentially argued that the laws of physics must contain a hidden rule, a cosmic safety mechanism that prevents closed time-like curves from ever forming in the real world. He suggested that quantum effects, the wild and unpredictable behavior of particles at the smallest scales, would always conspire to disrupt the conditions needed for a time loop. Just as a time machine was about to activate, a surge of quantum energy would inevitably destroy it, preserving the linear flow of cause and effect that defines our reality. It is as if the universe is protecting its own history from tampering, ensuring that yesterday remains firmly in the past. So while the mathematics of general relativity generously offers us these incredible loops, the finer print of quantum physics might forever revoke the invitation. The door to the past may be locked not by a lack of power, but by the fundamental need for the universe to make sense. Yet the universe might hold particles that break this ultimate speed limit without any effort at all. Tachyons are a purely hypothetical class of particles born from the mathematics of special relativity. According to Einstein's own equations, any object with mass can only approach the speed of light, never reach it because its mass would become infinite. But what if a particle was born moving faster than light? Tachyons are theorized to be just that, forever locked into a superluminal existence. They would not accelerate to these speeds, they would simply always be there, incapable of slowing down to the pedestrian pace of light. Their most bizarre property is how they would experience time. For us, as we move faster, time slows down. For a tachyon, moving even faster would mean its internal clock would not just slow but run backwards. From its own perspective, it might be traveling from the future into the past. Imagine a tachyon message beam. You could fire a stream of these particles, and from your point of view, they would be received by someone before you even decided to send them. This would open the door to sending information, perhaps even objects, backwards through time. The implications are staggering. A future civilization could use tachyons to warn us of an impending disaster, or a historian could receive first-hand accounts from ancient Rome. For decades, physicists have searched for signs of these phantom particles in the debris of high-energy cosmic ray collisions and particle accelerator experiments. They have looked for unusual patterns of energy loss that would betray the presence of a particle moving faster than light. So far, every search has come up empty. The silence is deafening. The major theoretical hurdle is causality itself. If you can send a message to your own past, you create the same paradoxes we fear with other forms of time travel. What if the message you receive instructs you never to build the tachyon communicator in the first place? The universe seems to have a deep-seated preference for a stable timeline, and tachyons threaten to unravel that completely. They remain a fascinating ghost in the machine of physics, a reminder that the laws of the cosmos might permit wonders we cannot yet imagine, or perhaps they stand as eternal guardians, forbidding us from tampering with the one-way flow of time. Perhaps the universe possesses a kind of immune system, a fundamental law that protects the timeline from the chaos of paradox. This is the elegant and somewhat unsettling idea behind the Novikov self-consistency principle, proposed by the Russian astrophysicist Igor Novikov. It states with simple finality that any actions taken by a time traveler were always a part of history. You cannot change the past because your very presence in the past is what caused events to unfold exactly as they always did. Think of time not as a line you can redraw, but as a perfect, unbreakable loop. Your journey to the past is not an intrusion, it is a feature, an integral component of the history you remember. Imagine traveling back to prevent a famous assassination. You hide in the shadows, ready to tackle the assailant, but at the crucial moment, you accidentally knock over a trash can. The noise startles a nearby flock of pigeons, causing the assassin to look up and adjust his aim at the last second, ensuring the fatal shot lands true. Your attempt to stop the event was the very thing that guaranteed its success. The timeline remains consistent, and your free will was merely an illusion, a predetermined part of a cosmic script. This principle neatly dissolves the terrifying logic of the grandfather paradox. If you go back in time with the intention of preventing your grandfather from meeting your grandmother, something will always intervene. Perhaps you get lost on the way, maybe you have a sudden change of heart, or in a cruel twist, you are the one who introduces them, making your own existence possible through the very act of trying to erase it. Your actions in the past are not creating a new future, they are fulfilling the one that already exists, a future that includes your journey back. This offers a clean, paradox-free solution to time travel, but it comes at a profound cost. It suggests that our lives are on a single, unalterable track. Every choice you believe you are making has already been made. Every journey you might one day take has already happened. You are not the author of your story, but an actor reading lines written before you were born. The freedom to change things, to fix mistakes, is replaced by the certainty that every mistake was necessary. The universe, it seems, prefers a good story to a messy one, and it will not allow anyone, not even a time traveler, to ruin the plot. Our persistent sense of moving through time might be the grandest illusion of all. The block universe theory proposes that past, present, and future are not successive states but exist simultaneously, fixed forever in a vast four-dimensional structure. Think of reality not as a flowing river but as a whole loaf of bread. Every slice of that loaf, from the crust of the Big Bang to the crumb of the distant future, is equally real and present. You are simply conscious of one slice at a time, experiencing the illusion of progression as your awareness moves along the loaf. This is not just philosophical speculation, it is a direct interpretation of Einstein's own work. In his theory of relativity, he fused space and time into a single entity called spacetime. Just as all points in space coexist, so do all moments in time. Your birth, your life, and your final breath are all out there, permanent coordinates in the cosmic block. So what would time travel be in such a universe? It would not be changing history. It would be a journey, much like moving from one city to another. You would simply be accessing a different set of coordinates within the static structure. A time machine would be less like a magical device and more like a subway car, transporting you from the station of today to the station of yesterday. Your past self is still there, living their life just as you are here, living yours. You would not be rewriting the story. You would just be turning to a different page in a book that has already been fully written. This view carries a profound and unsettling philosophical weight. If every moment is predetermined and eternally fixed, then what becomes of free will? Are our choices real, or are we merely following a script, our consciousness tracing a path that was carved into the cosmos from the very beginning? Your feeling of deciding to watch this video was inevitable, a note in a symphony that was composed at the dawn of time. This can feel like a lonely, deterministic prison, but it also offers a strange kind of comfort. Every mistake you have ever made, every moment of joy or sorrow, is a permanent and necessary part of the whole. Nothing is ever truly lost. The entire tapestry of existence, from the fall of empires to the quiet smile you had this morning, is forever real, forever preserved in the unchangeable block of spacetime. The journey through time becomes a tour of a magnificent, completed museum, where every exhibit is eternally on display. While the block universe presents time as a static sculpture, a strange new form of matter suggests time might have a rhythm all its own. These are time crystals, a discovery so bizarre it redefines what we consider a phase of matter. You are familiar with the classic states, solid, liquid, and gas, where atoms arrange themselves in different spatial patterns. A time crystal is different. Its atoms are locked in a pattern that repeats not in space but in time. Imagine a diamond that, instead of being still, constantly wobbles or ticks like a clock, returning to its original configuration over and over again. The most astonishing part is that this ticking happens in its ground state, the lowest energy level possible. It does this without consuming any energy, forever oscillating without ever winding down, a perpetual motion machine at the quantum scale. This breaks a fundamental symmetry of the universe known as time translation symmetry, the idea that the laws of physics are the same at every moment. For a time crystal, one moment is not the same as the next. Its state is intrinsically tied to a specific phase in its cycle. It is a system forever out of equilibrium, dancing to a beat that the rest of the universe cannot hear. How could this lead to controlling time? The connection is highly speculative but captivating. If we can learn to manipulate these temporal patterns, we might one day learn to synchronize them or even imprint information onto their rhythmic cycles. A network of time crystals could act as a kind of quantum clock, not just measuring time, but perhaps interacting with its flow. Think of it as learning the secret frequencies of time itself. A device built on these principles might be able to create localized pockets where time flows at a different rate, or even detect the subtle temporal echoes of events. This is not about building a time machine in the classic sense, but about developing a technology that has a dialogue with time, one tick of a time crystal at a time. Researchers have already created primitive time crystals in labs, using chains of ions or dense clouds of atoms chilled to near absolute zero. They nudge the system, and it responds by oscillating at a different period than the nudge, a signature of its unique, broken symmetry. We are only at the very beginning of understanding this new frontier. The dream is that by mastering these non-equilibrium systems, we might uncover new laws of physics that govern temporal structure, moving from being passive passengers in time to active participants in its grand, unfolding rhythm. But what if the flow of time is not a river we float on, but a reality we help to create? This brings us to one of the most mind-bending and controversial ideas, the anthropic principle. In its simplest form, it asks why the universe seems so perfectly fine-tuned for our existence. The constants of nature, the strength of gravity, the mass of an electron, appear to be set with incredible precision. If they were even slightly different, stars would not form, complex chemistry would be impossible, and life could never arise. The weak anthropic principle offers a straightforward answer. We should not be surprised to find ourselves in a universe that can support us, because if it did not, we would not be here to be surprised. It is a simple, almost tautological observation about our place in the cosmos. But a more radical version, the participatory anthropic principle, takes this much further. It was proposed by the physicist John Archibald Wheeler, who suggested that observers are necessary to bring the universe into being. He envisioned a cosmos where the past is not fixed until it is observed in the present. In this view, the universe only becomes concrete, only settles on one specific history when a conscious mind looks back and measures it. This connects directly to the strange world of quantum mechanics, where a particle exists in many possible states until it is observed and forced to choose one. Wheeler speculated that we, through the act of observation, are retroactively determining what happened at the Big Bang. Our present consciousness is, in a sense, creating the past. From this speculative foundation, an even wilder idea emerges. If consciousness plays such a fundamental role in shaping reality, could it also influence our personal experience of time? Could focused intent or deep meditation allow a mind to shift its own temporal experience, effectively traveling mentally through time? The theory suggests that by altering our state of consciousness, we might be able to access information from the past or future, not by moving our bodies, but by tuning our minds to a different frequency of the timeline. Imagine a form of mental time travel where profound concentration allows you to experience events from history as if you were there, or to receive intuitive glimpses of future possibilities. This is not about physics or engineering, but about the potential power of the mind to navigate the block universe. Of course, this remains one of the most contentious ideas on our list. It strays far from testable, repeatable science and into the realms of philosophy and metaphysics. There is no laboratory evidence that human intention can bend the flow of time, and the concept is often dismissed as pseudoscience. Yet it persists because it touches on a deep, unresolved mystery, the hard problem of consciousness. Why do we have subjective experience at all, and what is its true relationship with the physical world? The anthropic principle, in its most radical form, places us not as passive passengers in time, but as active participants in the very creation of the cosmos. It suggests that the ultimate time machine might not be found in a laboratory, but within the silent, observing space of our own minds. If a black hole is a cosmic drain from which nothing returns, then its theoretical twin is a celestial fountain. This is the white hole, a bizarre and beautiful prediction of Einstein's equations. While a black hole's event horizon is a point of no entry for anything outside, a white hole's horizon is a point of no exit for anything inside. It is a region of spacetime that violently expels matter and light but cannot be entered from the external universe. The mathematics of general relativity treats time as symmetrical, and if you were to run the equations for a black hole backwards, you would get a white hole. They are two sides of the same coin, one swallowing everything, the other spewing it out. This symmetry suggests a tantalizing possibility. Could the swirling vortex of a Kerr black hole, with its ring singularity, be connected to a white hole elsewhere? One might serve as the entrance to a tunnel and the other as the exit. Falling into a specific type of black hole might not lead to crushing death, but to a spectacular rebirth as you are ejected from a white hole in a different time or even a different universe entirely. You would be spat out into a new reality, having traveled across a bridge forged by gravity's most extreme forces. Yet for all their mathematical elegance, we have never observed a white hole. They are considered highly unstable if they can form at all. A common hypothesis is that a white hole would instantly collapse under the influence of any matter or energy falling onto it, effectively transforming back into a black hole. Their existence remains a ghost in the machine of theoretical physics, but one of the most profound speculations is that we have already witnessed the greatest white hole of all. The Big Bang, the explosive birth of our entire cosmos, shares a stunning resemblance with a white hole event. It was a singular moment when all the energy and matter in the universe erupted from an infinitesimal point, an ultimate expulsion that could never be reversed. If this is true, then our entire universe might be the output of a primordial white hole, the other end of a cosmic tunnel from a reality we can never know. Traversing such an object would be the ultimate form of time travel, not merely moving through years or centuries, but crossing the threshold of creation itself. You would be hurled back to the very beginning, a witness to the first moment. But what would you find there? A deterministic clockwork or a seething quantum foam where time has no meaning? The white hole remains a monument to the beautiful, unproven symmetries hidden within the heart of gravity. This is the bootstrap paradox, a loop of cause and effect with no true beginning. Imagine you are a brilliant inventor, but you are struggling to finish the blueprints for your time machine. One day, an older version of you appears, handing you a complete and perfect set of plans. You use these plans to build the machine, you grow older, and eventually you travel back to give those very same plans to your younger self. Where did the design for the time machine originally come from? It was never invented, only endlessly recycled. The information exists in a perfect closed loop without any point of creation. This is not just a story about blueprints. Think of a composer who hears a beautiful, unknown symphony in their head. They write it down and publish it, and the music becomes a timeless classic. Later, they travel back in time and hand the sheet music to a young Beethoven, who then composes the very same symphony which the time traveler eventually hears. The music has no author, no moment of inspiration. It simply always was. This paradox does not necessarily break the laws of physics. An object or piece of information trapped in a causal loop is entirely self-consistent. It does not appear from nothing, it eternally exists. The universe's books remain balanced. The violation is not of physical law, but of our deep-seated intuition about origins. We are conditioned to believe that everything has a cause, a starting point. The bootstrap paradox shatters that belief, presenting a reality where some things might just be, with no prior cause, forever locked in a dance of their own making. Could this explain some of the strange consistencies we see in the cosmos? Perhaps a fundamental constant of nature is not a fundamental truth, but a piece of information caught in an unimaginably vast causal loop, set in motion by a time traveler from the end of the universe. The loop is perfectly stable, a story that writes itself over and over, leaving us to wonder if we are merely discovering truths that were always destined to be found, in a circle with no end and no beginning. Two particles born from the same quantum event can become entwined in a bond that distance cannot break. This is quantum entanglement, a phenomenon so strange that even Einstein called it spooky action at a distance. When two particles are entangled, measuring the property of one, such as its spin, instantly determines the property of the other, no matter if they are inches apart or on opposite sides of the galaxy. This instantaneous connection seems to bypass the normal flow of information, defying our classical understanding of space and time. This is the principle of non-locality, where the universe appears to be interconnected in a way that transcends the speed of light. If you change one particle here, its partner reacts now, not later, as if space between them does not truly exist. This immediate link forces us to ask a radical question. Could this spooky connection also transcend time? Some interpretations of quantum mechanics suggest that the present can reach back and influence the past. One of the most compelling clues comes from an experiment known as the delayed choice quantum eraser. In this mind-bending setup, a single photon is sent through a special apparatus. It has a choice to behave either as a particle taking a single path or as a wave taking multiple paths simultaneously. The truly bizarre part happens later. After the photon has already made its journey and been detected, a decision is made at random to either observe which path it took or to erase that information. When scientists erase the which path information retroactively, the photon at the detector suddenly acts as if it traveled as a wave all along. It is as if the future choice reaches back in time and changes the past behavior of the particle. The event that happened later determines how the particle behaved earlier. This is not a flaw in the experiment, it is a repeatable result that challenges our deepest assumptions about cause and effect. Could this be harnessed? The tantalizing speculation is that by carefully manipulating a vast network of entangled particles, we might one day learn to send a simple signal backwards through time. Perhaps a future civilization could set up an entangled particle at its birth, and a past civilization could measure its partner, receiving a single bit of information from the future. This would not be a machine you step into, but a form of quantum communication across the ages. The reality, however, is far more complex and restrictive. The rules of quantum mechanics prevent us from using this to send useful messages or warnings into the past. The correlations between entangled particles appear random until they are compared with a classical signal sent at light speed, which defeats the purpose of faster-than-light communication. You might know what state your particle is in, but you cannot control it to send a deliberate message like a 1 or a 0. The universe seems to have built-in encryption, allowing for spooky connections but forbidding paradox-inducing time mail. Yet these experiments are not just curiosities, they are profound hints that at the quantum level, time may not be the one-way street we experience. The rigid sequence of past, present, and future might dissolve into a web of probabilistic connections where what happens now and what happens then are not so easily separated. We are peering at the very foundations of reality, where time itself may be an emergent property from a deeper, timeless quantum world. This infinite branching of reality is known as the multiverse. Here, every choice you make, every random quantum event does not just fade away. It spawns a new, parallel universe where the alternative outcome is real. In one world, you turned left, in another, you turned right, and that single decision cascaded into a completely different life. This is not merely a science fiction trope. It is a serious interpretation of quantum mechanics and a consequence of cosmological theories like eternal inflation, which suggest our Big Bang was just one bubble in a frothing, endless cosmic foam of universes, each with its own unique physical laws and history. Within this framework, time travel transforms entirely. You are not journeying back along a single, fragile timeline that you risk shattering with a misplaced footstep. Instead, you are shifting laterally, stepping sideways from your own branch of reality onto another. A time machine becomes a reality hopper. You could travel to a point labeled 1963, but you would not be arriving in your own past. You would be stepping into the past of a parallel Earth, a branch that split from your own the moment you appeared. In that world, you could witness history unfold differently. Perhaps you see a different outcome to a global conflict, or you find a world where a lost empire never fell. You could even meet alternate versions of yourself. The grandfather paradox becomes meaningless. If you were to find your ancestor in this new timeline, your actions would only affect that branch. The original universe you came from, with its unbroken chain of events leading to your birth, remains untouched and secure. This offers a kind of freedom that makes other forms of time travel seem perilous. You become an archaeologist of possibility, exploring the infinite museum of what might have been. Yet this freedom comes with a profound sense of scale. If every possibility is realized somewhere, then every triumph and every tragedy is eternally happening. For every version of you that finds happiness, another faces despair. The multiverse does not just resolve paradoxes, it presents a cosmos of endless stories where you are both the author and a single, fleeting sentence in a library of infinite books. Kurt Gödel, the famed logician, presented a universe where you could travel to the past on a rocket ship with no black holes or wormholes required. His solution to Einstein's own equations of general relativity described a cosmos that was not expanding but instead rotating as a whole. In this Gödel universe, every galaxy, every star is slowly swirling together in a grand cosmic waltz. This universal rotation has a profound effect on the fabric of spacetime, twisting it into global loops known as closed time-like curves. The principle is startlingly simple. If you were to embark on a sufficiently long journey through this rotating space, flying far enough along a specific path, you would eventually find that your trajectory through space-time had curved so dramatically that it looped back on itself. You would return to your starting point in space, but also to a moment in time before you ever left. The entire universe becomes a natural time machine, where a long voyage through the void is all it takes to meet your own past. This hypothetical cosmos also possesses a strange and uniform density, with no center to the rotation. Every observer on every world would feel themselves to be at the still center of a turning universe, with the distant stars slowly revolving around them. It is a perfectly self-consistent, albeit very alien, reality. Yet our own observable universe shows no signs of this overall spin. We see clear evidence of cosmic expansion, with galaxies rushing away from each other, and we have not detected the telltale twisting of starlight that such a universal rotation would produce. Gödel's model stands as a powerful mathematical proof, a gift from pure logic demonstrating that Einstein's theory does not forbid travel into the past. It shows that the laws of physics in a different kind of cosmos could allow for time travel on a truly cosmic scale, woven into the very fabric of existence itself. The universe we live in may not be Gödel's, but its existence in the realm of equations is a permanent reminder that the line between science fiction and science is drawn not by impossibility, but by the specific and perhaps local conditions of our reality. Stephen Hawking looked at these potential time loops and proposed a cosmic rule against them. He called it the chronology protection conjecture, a simple but profound idea that the laws of physics fundamentally forbid time travel to the past. His reasoning was not based on a lack of mathematical possibility, but on a need to protect reality from itself. Hawking essentially argued that the universe has a built-in immune system, one that violently rejects paradox. He suggested that any attempt to create a closed time-like curve, the kind of path that leads back to your own past, would trigger a catastrophic quantum reaction. Just as a time machine was about to become operational, the empty space around it, the quantum vacuum, would rebel. This vacuum is not truly empty. It is a seething foam of virtual particles popping in and out of existence. Under normal conditions, these fluctuations are harmless, but near a forming time machine, the extreme warping of spacetime would amplify them beyond control. These quantum fluctuations would escalate into an infinite surge of energy, a feedback loop of raw power that would literally destroy the machine before it could ever be used. It would be like a cosmic circuit breaker tripping, preventing a short circuit that would fry the entire timeline. This is the ultimate form of cosmic censorship, not for black holes but for time itself. The past is declared a protected zone, permanently off limits to tourists from the future. The principle of causality, the unbreakable chain of cause and effect that gives our lives meaning and order, is thus preserved from meddling. Your past actions remain your own, safe from interference by your future self. Yet this grand prohibition is, for now, just a compelling conjecture. It is a powerful argument from one of our greatest minds, but it is not a proven law of nature. Some physicists argue that we do not yet have a complete theory of quantum gravity, and that such a theory might reveal a way to stabilize these loops without triggering a vacuum catastrophe. Other theories, like the many worlds interpretation, might offer loopholes by allowing travel to parallel pasts instead of our own. Hawking's conjecture stands as a formidable theoretical barrier, a guardian at the gate of history. It suggests that the universe might value a consistent story above all else, and that it will fight to keep its narrative clean. The door to yesterday may be locked not by our ignorance, but by the universe's profound need to make sense. Deep beneath the smooth predictions of general relativity lies a seething, chaotic ocean. At the tiniest imaginable scale, the Planck scale, spacetime itself is thought to boil with a violent froth. Here, the very concepts of before and after may lose all meaning. The Planck length is an almost inconceivably small unit, about 1 trillion times smaller than a proton. At this scale, the smooth fabric of spacetime described by Einstein is believed to break down into a turbulent sea of virtual particles and wormholes, constantly flickering in and out of existence. This is the quantum foam, the fundamental texture of reality. Within this foam, the geometry of spacetime is not smooth and continuous, but granular and discrete, composed of tiny, indivisible loops or strings. This is the frontier of quantum gravity, the long-sought theory to unite the cosmic laws of general relativity with the probabilistic rules of the quantum world. Two leading approaches, loop quantum gravity and string theory, offer different visions of this underlying structure. Loop quantum gravity proposes that space is woven from a network of finite, one-dimensional loops like an unimaginably fine mesh. In this view, time might also emerge from the changing relationships between these loops. String theory, on the other hand, suggests that the fundamental entities are not point particles but tiny, vibrating strings, and that spacetime has many more dimensions than the four we experience. The vibrations of these strings determine the properties of all particles and forces. The dream of a theory of everything is that it would finally describe the physics of this quantum foam, revealing how spacetime is built from the ground up. And if we could understand its architecture, could we learn to rewire it? The speculative leap is that a sufficiently advanced technology might manipulate these Planck scale structures. By exciting the quantum foam in just the right way, we might be able to stabilize one of those naturally occurring, fleeting wormholes, weaving it into a permanent tunnel. Or we might twist the loops of space to create a closed timelike curve, a stable loop in time itself at the most fundamental level. This would not be time travel built with massive cylinders or warp drives, but time travel engineered at the root of reality. It would be like learning the source code of the universe and writing a new command into it. The power to command time would then be the ultimate expression of understanding, a mastery over the very pixels that compose existence. Yet this vision remains a distant dream, for we are still centuries, perhaps millennia, from a complete theory of quantum gravity, let alone the godlike technology to manipulate its fabric. This idea suggests the universe we perceive might be a magnificent illusion. The holographic principle proposes that all the information contained within any volume of space, including the events unfolding within it, can be entirely encoded on its two-dimensional boundary. Think of it like a cosmic DVD. The rich, three-dimensional movie you experience is actually stored as flat data on the surface of the disk. In this radical view, our seemingly solid, three-dimensional reality, with its passage of time, could be a projection from a vast, distant screen where the true, fundamental laws of physics reside. This concept emerged from the study of black holes and the nature of information. When an object falls into a black hole, what happens to the information it contains? The laws of quantum mechanics insist that information can never be truly destroyed. The holographic principle offers a solution, suggesting that all the information about what falls in is not lost inside the singularity, but is instead smeared and preserved on the black hole's event horizon, the point of no return. This is the ultimate cosmic hard drive, a perfect record etched onto a two-dimensional surface. This profound link between a volume and its boundary is mathematically described by the AD/CFT correspondence, a powerful concept in theoretical physics that bridges the gap between gravity, which governs the cosmos, and quantum field theories, which describe particles. It shows that a theory of gravity in a bulk volume of space is equivalent to a quantum theory without gravity living on its boundary. The most staggering implication for time is that it may not be a fundamental feature of the universe. If our three-dimensional reality is a projection, then time itself, our relentless forward march, could be an emergent property, a side effect of how this holographic data is processed and displayed. We are not moving through time, we are reading the data in sequence. So what would time travel be in such a universe? It would not involve rockets or wormholes, but a form of supreme information technology. A civilization that mastered the holographic code could, in theory, access any moment in the past or future the same way a computer programmer accesses a saved file. You would not journey to ancient Rome, you would simply call up its data from the cosmic storage and project yourself into that reality. Changing the past would be a matter of rewriting the information on the boundary, editing the source code of history itself. This suggests a future where time travel is not an engineering problem, but a computational one. The ultimate time machine might look less like the TARDIS and more like a quantum supercomputer of unimaginable power, one capable of interacting with the foundational layer of reality. The power to command time would be the power to reprogram the universe, but this raises a haunting question. If we are just data on a cosmic screen, who or what is running the simulation? The relentless acceleration of the cosmos may hold a key to time itself. Dark energy is the name we give to the mysterious force that is not just expanding the universe, but causing that expansion to speed up. Imagine a car that keeps pressing its own accelerator pedal faster and faster with no driver in sight. This is the effect dark energy has on the very fabric of space-time, pushing galaxies apart at an ever-increasing rate. We cannot see it or touch it, but we can observe its profound influence on the largest scales of existence. Now, consider what this accelerating expansion means for the flow of time. The universe has a kind of clock, a grand rhythm set by its expansion, which we could call cosmic time. But within this vast, stretching canvas, local regions could, in theory, experience time differently. If we could somehow harness or manipulate dark energy, we might be able to create a localized bubble where the expansion rate is artificially increased or decreased. Inside a pocket of hyper-accelerated expansion, space-time itself would be stretching faster than the world outside. Time, which is inextricably linked to that space-time, might also appear to speed up from an external perspective. An hour spent inside such a bubble could see 1,000 years pass in the outside universe, effectively launching anyone within it on a one-way journey into the far future. You would not be moving through time, but rather, time would be carrying you forward on a swift local current. Conversely, creating a region where expansion is halted, a still pocket in an inflating cosmos, could slow local time to a crawl relative to the outside. The engineering required for such a feat is so far beyond us it might as well be magic. We do not even know what dark energy is, let alone how to bottle it. It could be a property of the vacuum of space, a new kind of field, or evidence that our understanding of gravity is incomplete. The very idea of controlling it is a leap into the deepest unknowns. Yet, the tantalizing possibility remains that the force driving the universe apart could also be the engine for the most profound form of time travel, a journey powered not by gravity, but by the silent, relentless breath of the cosmos. This strange quantum quirk is happening all around you, unnoticed in the empty spaces between atoms. The vacuum of space is not truly empty, but a seething sea of virtual particles that flicker in and out of existence, borrowing energy from the future for a fleeting moment before vanishing back into nothingness. This quantum frenzy creates a subtle pressure even in the void. Now, bring two perfectly smooth, uncharged metal plates incredibly close together in this vacuum, so close that only the tiniest wavelengths of this quantum foam can fit between them. Outside the plates, a riot of larger wavelengths can still exist, but inside that narrow gap, the longer waves are excluded. The result is that the pressure outside the plates becomes greater than the pressure inside, and the plates are pushed together by the sheer force of nothingness itself. This is the Casimir effect, a proven and measurable phenomenon that demonstrates the bizarre reality of quantum fluctuations. The energy state between those plates is lower than the energy of the pure vacuum outside, a condition physicists describe as negative energy density. It is a tiny, localized patch of the universe where the energy is, in a sense, less than zero. This is not just a theoretical curiosity, it is the very substance we have been searching for. Remember the exotic matter needed to prop open a wormhole or power an Alcubierre warp drive. That hypothetical material with anti-gravitational properties requires this exact quality, negative energy density. The Casimir effect proves that such an energy state is not just a fantasy, it is a real, physical effect we can create in a laboratory. Scientists have measured this force between plates separated by mere nanometers, a distance smaller than a wavelength of light. The force is minuscule, but it is undeniably there, a whisper from the quantum world that spacetime can be manipulated. The monumental challenge, of course, is one of scale. The energy we generate in these experiments is infinitesimally small. To warp spacetime on a scale large enough for a person or a spacecraft to pass through, we would need to generate a titanic field of this negative energy. Imagine trying to power a city by harnessing the static electricity from a single sock fresh out of the dryer. The gap between our current capabilities and what would be required is almost beyond imagination. We would need to engineer structures of immense size and perfect smoothness, maintain microscopic vacuums over vast areas, and find a way to amplify this quantum whisper into a cosmic shout. Yet the principle stands firm. The Casimir effect is a direct physical demonstration that we can, in a limited way, engineer the vacuum itself. It suggests that the key to bending spacetime might not lie in colossal cosmic strings or infinite cylinders, but in mastering the ghostly, fleeting dance of the quantum world. If we could ever learn to scale this effect, to weave threads of negative energy into a stable fabric, we might finally hold the tools to build a doorway not just to other stars but to other times. The grandfather paradox is the ultimate test for any time travel theory. You journey to the past and commit a single, irreversible act, the murder of your own grandfather before he has children. This creates an impossible logical loop. If you succeed, you are never born, which means you could never have traveled back to commit the crime in the first place. So how could the murder ever happen? This is not just a plot hole for science fiction. It strikes at the very heart of causality, the principle that cause must always come before effect. If time travel to the past is possible, our entire understanding of a rational, ordered universe collapses. Yet several compelling resolutions offer a way out. We have already seen how the many worlds theory sidesteps the issue by having you jump to a parallel timeline, and how the Novikov principle enforces a predestined loop where your actions always fail. But there are other fascinating possibilities. One suggests the universe possesses a kind of subtle immune system. You might travel back with the clearest intention, but something will always intervene. You take aim at your grandfather, but your gun jams. You try to push him off a ledge, but you slip on a patch of ice. A sudden noise distracts you at the crucial moment. The universe self-corrects through a cascade of seemingly random, unforeseen events, preserving the timeline not through a grand law, but through a million tiny accidents. Another idea proposes a more direct physical law, that time travelers are simply unable to change key historical events. Perhaps the very atoms of your body become locked in place when you near a paradox-inducing action, a kind of temporal paralysis. Or maybe your consciousness is shielded, making you an observer who can see and hear the past but never truly interact with it, a ghost in your own history. The central role of this paradox is undeniable. It forces us to choose what kind of universe we live in. Is it one of rigid, unchangeable history? Is it a multiverse of infinite possibilities where every mistake is made somewhere? Or is it a clever, adaptive system that protects its own consistency at all costs? Your answer to the grandfather paradox defines not just the mechanics of time, but the very nature of reality itself. We treat the three dimensions of space as our natural home, moving forward and back, left and right, up and down with intuitive ease. But what if time is simply the next direction on that list, a fourth dimension just as real as the others? In this view, the entire universe is a single, solid block of four-dimensional spacetime, a concept we have already touched upon. Your life is not a series of fleeting moments, but a long, winding worm through this block, a permanent sculpture from birth to death. Navigating time would then be less about breaking the rules and more about learning to move in a direction we have not yet mastered. Think of Edwin Abbott's classic tale, Flatland. The inhabitants of that world are two-dimensional shapes living on a flat plane. They can perceive left and right, forward and back, but the concept of up is utterly alien to them. If a three-dimensional object, like a sphere, were to pass through their plane, they would not see the whole sphere. They would only witness a mysterious series of changes, a point that grows into a circle and then shrinks back to a point. Their limited senses render the higher dimension as a sequence of inexplicable miracles. We are the flatlanders of time. We perceive our existence as a single, unchanging point we call the present, sliding along the timeline. But a being that existed in four spatial dimensions would see our entire timeline laid out at once, from our first breath to our last. To such a hyper-being, traveling to a different point in our history would be as simple as we walking from one room to another. They could look at the adult you and the child you simultaneously, just as we can see both ends of a long rod at the same time. So what would a technology for this kind of travel look like? It might not be a machine that punches a hole in reality, but a vehicle that can rotate and move along the time axis. We might call it a time plane, a craft that can lift off from the present and cruise through the time dimension. To steer it, you would need a sense we completely lack, a temporal sense of direction. Just as we have an internal sense of balance for up and down, a time pilot would need to develop a feeling for then and when. They would need to perceive the entire timeline as a landscape, seeing the rise and fall of civilizations not as history, but as topography, with mountains of great achievement and valleys of quiet years. This leads to the even more dizzying idea of hyper-time. If our timeline is a single line in a four-dimensional block, perhaps that entire block is just one slice of a five-dimensional reality where every possible version of our timeline exists side by side. Moving through hyper-time would allow you to shift between different histories, selecting the branch where you made a different choice or where a world event had an alternate outcome. The skills required for this are almost beyond our comprehension. You would need a mind capable of holding multiple, contradictory truths at once, seeing the you who succeeded and the you who failed as equally real. Your consciousness would have to expand to perceive not just what is, but what could have been and what might yet be. The journey from being a prisoner of the present to a navigator of time is the ultimate frontier, not of space, but of perception itself. Electromagnetic waves might be secretly traveling in both directions through time. This is the radical heart of the Wheeler-Feynman absorber theory, a bold reimagining of how light and matter interact. In the 1940s, physicists John Wheeler and Richard Feynman asked a deceptively simple question. When an electron jiggles and emits a photon, where does the energy for that wave ultimately go? The standard answer is that the wave radiates outward forever, its energy dissipating into the infinite cosmos, but Wheeler and Feynman found this unsatisfying. They proposed a more elegant, symmetrical solution. They argued that the electron's jiggle produces not one wave, but two. The first is the familiar retarded wave, which travels forward in time, the kind we see as light and radio signals. The second is an advanced wave, traveling backward in time from all the future particles that will ever absorb that energy. In this view, an atom only shines because the entire future universe is already there to catch its light, sending a confirmation signal backwards to authorize the emission in the first place. It is a cosmic handshake across time where the future reaches back to influence the past. This completes the circuit of cause and effect in a perfectly balanced loop. The theory was initially developed to solve a thorny problem in classical electrodynamics, but its implications resonate deeply with the quantum world. It provides a formal foundation for the transactional interpretation of quantum mechanics. In this interpretation, a particle like an electron sends out an offer wave into the future. All possible paths are explored. Then, from the future, a confirmation wave returns along a single, chosen path, finalizing the transaction and collapsing the probability cloud. The present moment is thus shaped by a negotiation between the past and the future. This is not mere philosophy, it is a mathematical framework that treats time as fundamentally symmetrical. It suggests that backward causation is not a logical flaw, but a necessary part of physical law. The universe may be a single, self-consistent whole where every event is interlocked across time, a vast tapestry where the threads from the future are just as real as the threads from the past. If this is true, then the flow of time we feel so acutely might be the result of this constant, invisible dialogue, a dance of waves where every cause has an effect, and every effect also has a cause reaching gracefully into the past. The world around you might be the most sophisticated video game ever created. This is the simulation hypothesis, a theory suggesting our entire universe, with all its history and complexity, is a digital construct running on some unimaginably advanced computer. If this is true, then the rigid laws of physics we struggle against are not fundamental truths, but merely the programmed rules of the simulation. And if you can understand the code, you can change the rules, including the rule that time only moves forward. Time travel in a simulated reality would not require wormholes or warp drives. It would be a matter of software. You could rewind the cosmic clock to a previous save state, effectively restoring the universe to a point in its past. You could fast forward, skipping ahead to see the outcome of any event. Or you could create a fork, a branch in the timeline, and run multiple versions of history simultaneously to observe different outcomes. This is exactly what video game developers do every day. They can roll back a game world to a prior state to fix a bug, or they can create multiple save files to explore different story paths without affecting their main playthrough. In our reality, such power would make you a god of time. You could revisit any moment in your life not as a memory, but as a living, interactive experience. You could correct a single, painful mistake with the ease of loading an old file. You could witness the construction of the pyramids or the courts of ancient empires by simply calling up the correct timestamp in the cosmic database. But this divine power carries terrifying responsibilities. If you can alter the past, do you have the right to do so? Changing one variable could have cascading, unforeseen consequences, potentially erasing entire lives from existence in the new timeline. And who gets to control the console? If one person or group gains this ability, they could rewrite history to suit their own desires, imposing a single, curated version of reality on everyone else. The simulation hypothesis remains firmly in the realm of metaphysics. There is no scientific experiment that can prove we are living in a simulation, as any result could be explained as part of the program. Yet it forces a profound philosophical question. If our reality is just information, then are we the players or are we merely characters in the game? Our sense of free will just an elegant illusion in the code. The ultimate time machine might not be found in a lab, but in the command line of the universe itself. The most accessible form of time travel might not require a machine, but a medical procedure. Instead of manipulating the cosmos, we could simply put our own biology on pause. This is the promise of biological time travel through cryonics or advanced suspended animation, a method that allows a person to leap into the future by slowing their metabolism to an imperceptible crawl. Imagine being frozen or placed into a state of profound hibernation after being diagnosed with an incurable disease. You are stored in a state of biostasis where decades or even centuries pass in the outside world. When a cure is finally discovered, you are revived. To your perception, only an instant has passed, yet you have arrived in a new era, having skipped over the entire intervening period. This is not science fiction. The field of cryopreservation already exists today, with several organizations offering to preserve legally deceased individuals at extremely low temperatures in the hope that future medical science can restore them to life and health. The central challenge is one of preservation without damage. When tissues freeze, the formation of ice crystals can shred cell membranes, causing catastrophic and irreversible harm. Modern cryonics aims to prevent this by using special chemicals called cryoprotectants, which act like biological antifreeze, vitrifying the tissues into a glass-like state without destructive ice formation. Scientists have successfully revived small organisms like tiny worms after cryopreservation, and research continues to push the boundaries of what can be preserved and recovered. A parallel path explores hibernation induction, mimicking the natural state seen in bears and ground squirrels. Researchers are actively studying the genetic and metabolic triggers that allow these animals to dramatically lower their body temperature and slow their vital functions for months, emerging with minimal muscle and bone loss. The goal is to one day induce a similar, safe torpor state in humans, which would be revolutionary for long-duration space travel, allowing crews to sleep through the years-long journey to another star system. For them, the voyage would feel brief, while centuries might pass back on Earth. This method is arguably the most feasible form of time travel we can conceptualize with our current technology. It does not violate any laws of physics or create causality paradoxes. It is a one-way ticket to the future, a patient waiting game where the traveler trades their present for a chance at a new tomorrow. But would the world you wake up in be a welcoming one? You would be a relic, a living fossil disconnected from everyone you ever knew, your culture and skills possibly obsolete. The journey through time is achieved, but the destination holds its own profound challenges. Your own mind is the most accessible time machine you will ever possess. We all have moments when time seems to warp, stretching a single minute of terror into an eternity or letting hours of joy vanish in a blink. This is not a flaw in reality, but a feature of your brain's perception. Psychological time is a river that flows at different speeds, and we are learning how to steer its current. Near-death experiences provide some of the most dramatic examples. People who have survived a fall or a cardiac arrest often report their entire lives flashing before their eyes in exquisite detail, a phenomenon known as life recall. But more fascinating is the sensation during the crisis itself, where seconds stretch out into what feels like long, contemplative minutes. A car crash victim might watch the windshield crack in slow motion, noticing every glittering shard of glass as it drifts through the air. This is likely the brain entering a state of hyper-awareness, flooding itself with neurotransmitters in a last-ditch effort to find a solution, effectively recording memories at an incredibly dense rate. When you play back such a densely packed recording, the event subjectively feels much longer than the clock time it actually occupied. We can chemically induce similar distortions. Psilocybin, the compound in certain mushrooms, and lysergic acid diethylamide, commonly known as LSD, can profoundly alter temporal perception. Users might feel trapped in a single, eternal moment or experience the sensation of lifetimes passing in an afternoon. These substances seem to disrupt the brain's default mode network, the part responsible for our sense of a continuous, linear self. When this narrator goes quiet, the brain's internal clock loses its rhythm, and moments can stretch, collapse, or loop without the usual constraints. But you do not need a brush with death or a powerful drug to bend time. Simple experiments in sensory deprivation reveal how fragile our perception truly is. In a flotation tank cut off from light, sound, and gravity, the brain, starved for external stimuli, turns inward. Without the steady tick of sensory input to mark the passage of seconds and minutes, your internal clock can drift wildly. An hour inside the tank might feel like 20 minutes or like 3 hours. The same principle applies to deep meditation. Advanced practitioners who can achieve states of profound focus report experiences of timelessness, where the constant chatter of past and future thought ceases and only a boundless present remains. This mastery over the mind leads to a tantalizing possibility, a form of purely subjective time travel. Through techniques like guided visualization or hypnotic regression, individuals can mentally revisit past memories with such vivid sensory detail that it feels like being there again. You can walk through the rooms of your childhood home, smell the rain on the pavement from a specific day, and feel the emotions you felt then. Conversely, you can project forward into detailed visions of the future, rehearsing a conversation or visualizing a goal with such intensity that it creates a powerful memory of an event that has not yet happened. This is not physical time travel, but for the conscious mind, the line between a memory and an actual past event can become beautifully blurred. If you can truly immerse yourself in a memory, are you not, in a very real sense, visiting the past? And if you can project a future self with such clarity that it guides your actions, are you not pulling a possible future into your present? Mastering the mind does not change the clock on the wall, but it changes our experience of the time we are given, offering the closest thing to a time machine that many of us may ever need. From the solid, proven warping of spacetime around a black hole to the wild possibility that our minds might one day navigate time itself, we have journeyed across 30 frontiers of human thought. Each theory, whether grounded in Einstein's robust equations or sprouting from the speculative soil of quantum foam, represents a profound effort to answer one of our oldest questions. We have seen time stretched by gravity, looped by cosmic strings, and potentially rewritten within a holographic code. While not a single one has been proven to allow human time travel, each idea serves a greater purpose, stretching the canvas of what we believe is possible and forcing us to rethink the very nature of reality. These are not just flights of fancy, they are serious exercises that pressure test our fundamental laws, revealing where our understanding is solid and where it crumbles into mystery. So now the question turns to you. Which of these 30 doors to the past or future resonates most deeply with you? Was it the paradoxical elegance of the Novikov principle or the infinite freedom of the multiverse? Share your favorite theory in the comments below and tell us which one you believe holds the most promise for our distant descendants. The search for time is far from over. It is an ever-unfolding mystery waiting for the next curious mind to take up the challenge. If exploring the enigmas of the cosmos fuels your imagination, subscribe for more deep dives into the universe's greatest secrets. Keep looking up and never stop wondering about the beautiful, bizarre possibilities hidden within the fabric of time.